The presence of the conjugate in what might be termed the official power formula, and that is the vector formula, is a mystery to most engineers. Now, what I mean by the official power formula is the vector version, which is S equals VI. Oftentimes we simplistically think of the power formula as P equals VI, but that is not the vector representation. In this particular formula that we're working with, it's important that we understand that we're both working with angles and magnitude. So S equals VI is a more physical and more real-world understanding of how power is measured and calculated, while P equals VI is more of an abstracted, simplified version of the power formula. So really what we're going to be talking about with the conjugate is going to be this S equals VI, not the P equals VI formula. And we know we have to use the conjugate, but we don't really understand what it accomplishes in a very fundamental sense. For example, if you think this graph properly represents this formula, you're wrong. It is a ridiculously common belief that the conjugate is used to flip the current vector across the voltage vector, just like this. But that's really not the case of what the conjugate does. You see, when working with power calculations like these, we are exploring the relative phase angle difference between voltage and current. If the conjugate just flips the current vector around the voltage vector, the relative angle difference is exactly the same. That is, the distance between the two vectors matches. They're exactly identical, meaning using the conjugate like this accomplishes absolutely nothing. So, if the conjugate accomplishes nothing, then why do we need to use it at all? Well, we know this conjugate formula is used for something. I mean, we all know that this exists, but what is it used for? The real issue behind all of this is when. When do we apply the S equals VI conjugate formula, as opposed to when do we need to apply the more simplified P equals VI formula? Well, when complex numbers are presented in the PE exam, unless otherwise very specifically indicated, the angle of the voltage will be zero, and whatever angle the current has will be relative to the voltage. So in this case, you would only really need to use the simplified P equals VI formula. The PE has set the question up to make the voltage vector at zero. However, occasionally the PE will test your knowledge of the conjugate. And the way you know they're doing this is they'll give you questions with voltage angles in the given values. So, if in the same question the current angle is given also, you should be aware these angles are absolute and not relative to each other. So let me say that real quick one more time. If the question provides you with voltage angles and it also gives you current angles, then the PE has not set up a relative difference, it has set up absolute angles. In that case, the P equals VI will not work. Instead, what you would have to do is you would have to either do some setup work to get the voltage vector to zero, or you can use the conjugate formula and you won't need to do any setup work at all, which is the preferred, more efficient way of working through your PE style question. The S equals VI conjugate formula begins in absolute scenarios. So we know the conjugate, graphically speaking, really means to pivot around the absolute x-axis. while the P equals VI formula begins in a relative scenario, a scenario assuming voltage to be the reference, which means that the conjugate in that circumstance accomplishes nothing, as we've already shown. So, if you're using P equals VI and entering in voltage angles in your calculations, it's very clear that you're doing it wrong. So, how does the conjugate help us deal with these absolute situations? To see this, let's consider the two ways voltage and current can be graphically represented in power calculations. These are the leading and lagging situations. Notice that the vectors shown here are absolute values. We need one single formula that can give us power under both of these absolute conditions. Since power is concerned with the relative angle difference between voltage and current, we need this one single formula to indicate the angles as that difference. Using the conjugate will give us that difference, while not using it will give us something completely useless. So let's demonstrate this first by showing the incorrect, non-conjugate formula applied to both leading and lagging. Now, buckle up and get your calculators because we're about to do some math. Phi here represents the relative angle difference between the voltage and the current vectors. The phi asterisk represents the angle difference between the original voltage vector and the conjugate of the current vector. The voltage and current variables are represented here, and A for these represents the magnitude of both of the vectors, while the theta represents the absolute angle of the vectors. And finally, I asterisk is the conjugate current, and the A and theta variables fall in line with the variables given above for voltage and current. These equations apply both to the leading and the lagging scenarios. We will continue on part 2 of this video series.